for each chapter?
That was my goal, and looking over it, yes, pretty even distribution. And frankly, even a chapter 5 question still references things from previous chapters. For example, I'm going to look at practice test number 10 real quick. This involves a basketball getting dropped off of a building. Its GPE turns into KE on the way down. That KE turns into EPE when the basketball temporarily pancakes against the floor. So I worked this showing energy transformations over time. But part A and possibly even part C can be done from the perspective of chapter 1 material. You could use the first 4 equations here to figure out A and C instead. So just because I think it's a chapter 5 question doesn't mean it has to be. Yes?
What does EPE stand for?
Elastic potential energy.
Okay.
Such as when I physically stretch the spring, I do work, I have used up energy, that energy is now in the spring in the form of elastic potential. And when I release the spring, that elastic potential is released to do something else.
And you said that turns into GPE?
So, kind of stepping through the stages of the ball's journey. Oh, we got pictures. The ball starts at rest 10 meters in the air. So here it has nothing but GPE. When you drop it, that GPE begins turning into KE on the way down because height decreases, velocity increases, until you reach this final point here, pausing time right before impact. We're as low as we're going to get, so height is 0, and we've reached top speed before impact. So freezing time right here, this is the moment where all the GPE is gone, and there's nothing left but KE. And so part A here is asking about the relationship between those 2 stages. What speed would it accelerate to at that point where all of the initial energy has become kinetic? Part B of this question references an additional point in time after that. Because if we unfreeze and allow it to actually collide with the floor, we can pause it again at the precise moment where velocity is 0, it is slowed down to a standstill, and in that moment it will squash slightly against the floor, which is what all elastic objects do on impact. It warps, it deforms for a split second. And in that moment, where it is slowed to 0, all of its kinetic energy would be gone, but it still doesn't have any GPE if it's on the floor. So in this moment, all it has left is EPE. All of the energy it had is now stored in its deformation. So all that energy is stored inside of it like a weird rubber battery. And then, if we unpause time again, it's going to spring back to normal and kick off the floor, turning that EPE back into KE, and then eventually GPE again as it rises. So a basketball bouncing is just a constant back and forth of GPE to KE to EPE to KE to GPE, so on and so forth. And so when I did my work here, the goal was to kind of demonstrate those energy transformations over time. The GPE becomes KE, that KE becomes EPE, that EPE turns back into GPE as we rise up to the same height if we didn't lose any energy.
I had a question unrelated to this.
Okay.
If there's any other questions in this one before.
Sorry, which one?
I was asking if anyone else had questions on this one.
Oh, okay.
Unrelated.
All right.
Am I able to draw something on the board?
Yeah.
To ask a question?
Just hope the marker you pick has ink in it.
there was one question, I don't know if it was on the practice test or what it was from, but I think it asked for like the magnitude and direction of the normal force, but like, what direction would this be? Is that like just 0 degrees north?
I'd call that positive Y.
Okay. 'Cause I just remember it said that like, what direction is this? And I wasn't sure if that's like 0 degrees, 180.
Yeah, up or positive Y or north, depending on your frame of reference. Trying to think.
I have no idea where that question came from.
That's fair. I asked about, was it this one?
Maybe. Yeah. I don't know.
That's fair. Yeah, normal force, well, the rule with normal force is a surface always has to create it, so like object sitting on surface. The surface is going to exert a force perpendicularly out of itself as a response to this object pushing into the surface. So if this box is sitting on flat ground and its own weight pushes down into the surface responds by exerting a normal force perpendicularly out of itself. So here, I would say that normal force would, in that scenario, if that is the overall picture, normal force points positive Y, alternatively up. Directly opposite gravity. Pardon. The main headache is if you are not on a flat surface, in which case normal force would point that way. Or rather, not on a horizontal leveled surface. Did I answer your question? Okay. Pardon.
Okay, in number 4, so we say that the force of the rope, but like the one with the flower pot is tension. Like,
Yeah,
what
you
is the
could.
difference between F of rope and tension?
There isn't one.
Okay.
It's just the name.
Because on that one, I started calling it F of rope, and I was like, well,
That is not wrong.
okay.
Tension is just a name for force pointing inward from either side of a rope. And that is exactly what is happening here. I don't know why I didn't call it tension, if I'm being honest.
Why and when can we assume that the tensions equal each other in like the rope problems?
Well, let's look at the flower pot, actually.
And the pulley one, the thing they equal each other.
Ah, good question. So, sorry, ask the question again. Want to make sure I answer it.
Why do we assume they equal each other, the tensions?
Well, in this scenario, okay, first assumption. What is the net force acting on this flower pot?
0.
0. And that is because it is being held in place. It is not accelerating. So even if the tensions didn't equal each other necessarily, which can happen if the angles don't match, the net force here is 0, meaning that everything must add up to 0, whatever each individual thing is. So that's the first thing that is part of the eventual assumption. Even if the angles don't match and all the tensions aren't exactly the same, they add up to 0 even if things are not moving, if things are not accelerating. And that is similarly true here in specifically the practice test version of this type of Pulley question, because ultimately in this Pulley question, nothing moves. Ultimately in this one, friction is strong enough to keep everything in place. Therefore, all of the net forces are zero, which tends to cause a lot of things to equal other things if there's only two forces that cancel out.
On this question, it has the friction, static friction greater than T, which is 50, but then it says that in the bottom left, the force of friction static is less than 55.
Correct. Less than or equal to.
And I'm just confused by that because then it says on the top right that
This is due to a weird quirk with static friction specifically. The formula for static friction, where this 55 came from, I didn't write out the formula. Is it on the formula sheet? Yes, it is, good. The official formula for static friction says that static friction is either less than or equal to normal force times mu s. And the reason for that is, it's because of static friction's job of stopping motion from starting. Let's say that the object we're studying is my calculator. How much static friction is currently needed to prevent this thing from moving with the current forces that are acting on it?
However much to overcome the static friction.
Well, what I'm asking is how much is the static friction? What static friction is currently acting on this thing? See, static friction's role is to stop motion from happening. Is there any motion attempting to happen right now? No, and for that reason, static friction is currently technically sitting at zero. Now, if we used this formula here, like say we knew the mu of the mu s for my calculator on this table, and we knew the normal force on the calculator, we could use this to find a number for the force of static friction, but currently none of that force is in use because none of it needs to be in use. The weird quirk with static friction is it only activates incrementally as is needed to keep something in place. Like, if the normal force on my calculator was 10 newtons and mu s was 0.5, then the maximum value of static friction would be 10 times 0.5 is 5 newtons. But that 5 newtons only activates incrementally as is required. Because right now there's no force trying to cause motion. If I come in here and I apply 1 newton to the right, 1 newton of the 5 will activate to cancel that. If I increase to 2, it'll increase to 2 in turn, up to the maximum of 5. And the object only begins moving if I overpower static friction's maximum. It only ever turns on as much as it needs to, because if it was just exerting 5 newtons in a direction right now, well, then the calculator would start moving because of friction. And that's the very antithesis to what friction is trying to do. So static friction only goes up to a certain maximum as is required. So all my work in this question was to figure out what is the maximum of static friction, and is the tension pulling the box forward greater than, equal to, or less than that maximum. So ultimately here, the maximum value for static friction, hence this symbol here, was 55 newtons, in comparison to a tension of 50 newtons trying to pull it forwards. That means that static friction can be bigger than the 50, so it doesn't move. And this is just a weird quirk of static uniquely. Kinetic, it's all or nothing. If you're in motion, kinetic is totally activated. Static's the only one that does this.
Are the test questions pretty much almost exactly like these kind of questions?
Not exactly. I always make the practice test longer and more difficult than the full test, because I'd rather you learn things and make mistakes here than on the actual test. Also, you can do the practice test comfortably in your dorm or with friends, and you have to do the test by yourself. For that reason, I make these longer and more difficult. Like there's a total of 16 questions on this thing, at least, including all the concept questions. Actual test is only 9. And I write the actual test questions with the idea that you are taking the test in a timed environment, and I am writing it such that I hope students would finish in an hour, or they could finish in an hour. I give you 3, but I write it as if you only had 1. For that reason, I write the test questions so that there's not as much sitting and staring at it until you figure out some key trick. And I also write them so that they don't all require an entire page of algebra just to get through. Like,
chapters 1 to 3, I feel good about. It's really just 4 and 5 that are making it work.
That's fair. Well, again, I'm trying to say this as a comfort. This took several lines of algebra, and it would take even more if the objects were in motion. Because we did this example in class where it was moving instead of being held in place. And when it was moving, we had to do the full 2 equations, 2 unknowns things across 3 axes in both objects. That took a lot of lines of algebra. I do not write my test questions to take that many lines of algebra because you're supposed to be able to do them quickly, like 1 question every 7 to 10 minutes. So I'm going to simplify my test questions so that they don't, so that the hard part isn't that they take forever. So keep that in mind.
Has everyone taken the whole time in the ones you proctored?
Of the 2, okay, I proctored on Wednesday. I didn't proctor Monday or Tuesday. On Wednesday, 1 person stayed until about 3:45, which would be 2 hours and 15 minutes. But I find that after about an hour and a half, that's the point where most students have already looked at everything, tried everything, and they're really just staring at it, racking their brains. Can I do better? And most students, I find, do the bulk of the work or their best work by an hour and a half. And the time that they stay after that is, sometimes it's academic accommodations. Some people just are meant to be taking the test for longer, but sometimes they just want to sit there and stare at it. And if they're willing to put that time in, I'm supposed to be in the building until 4:30 anyway. But if they're just sitting and staring at it, it's not really earning them as much points as the first hour where they were actually doing all their math. I don't think I've had anyone stay a full 3 hours, because again, you just kind of hit a point where you've done all you can, and you're really just bringing yourself to be able to turn it in emotionally. I don't recall anyone taking the full 3. Well, I take that back. When I began teaching here, I started teaching here full-time fall of 2019. And that semester I was co-teaching with a different professor. We each had different sections of 1500 that term. And that semester we tried a different test policy where rather than doing it during class or lab, we had everyone show up at a different third time. Like show up Thursday at 5:30 p.m. and everyone take it in the auditorium. And that time, students from the other section, from the other professor, stayed till like 10:30. But admittedly, an amount of that was just pointless chat. Like, they weren't talking about the test, but once the room got down to like the 3 people, they started like remarking, like just saying, chatting with each other in loud ways that had nothing to do with the test itself. Like, oh man, it's late, isn't it? Yeah, it's late. What'd you guys have for lunch?
They were just hanging out.
Kinda, yeah. Hanging out in a way that meant I didn't get home until midnight. But anyway. That is not the norm at all. Frankly, the exam I write to take 2 hours, most students have 3, and most people are comfortably done by the 2.5 hour mark. I'm just kind of rambling at this point. Did I answer the question?
I don't even remember the question.
That's fair. I write the test so that you can comfortably do it quickly, so that the trick to the test isn't meant to be, this problem is huge, spend all your time doing lines of algebra on it. I avoid that. And for that reason, I don't include questions that inherently take lots of time. I'm looking for your conceptual understanding, not your ability to just brute force algebra over 3 hours.
I've only heard scary things about this test so far.
Oh no. Well, to kind of oppose that perspective, of the ones I have finished grading, which is about 1/3 of the overall course, they're looking good. Like the average is sitting where it's meant to, low B, high C. Some people even, one person so far even got better than a 100. I am trying to say this as a comfort. Things are looking good, it's looking fine, and I am not worried about any given single student's performance. And I think you guys will do fine. I wouldn't write the test in a way that I didn't think you could honestly do it and be okay. My job is not to trick you. My job is for you to understand physics and not have the worst time of your life. So if you're miserable, I'm also probably miserable, unless I'm some kind of sycophant. Which I'm not. I don't know why I'm rambling like this at this point. I don't want you to have a bad time. I feel real bad when my students are frustrated. So I try to avoid that. I'm just monologuing at this point. How are you guys feeling, and what questions do you have?
If we can't assume that attentions equal each other.
Oh yeah, you did ask about that, sorry.
This is like the one in class, I'm pretty sure the one in class that they didn't equal each other.
Oh, like,
And then we just pretty much solved it using like.
You mean the one where like the one of the ropes was longer than the other?
Yeah. There's just a lot of math in my notes. It goes with this.
Yeah, in class we did, sorry, loading my PowerPoints. That's the wrong chapter 4.
Good one, chapter 4, are they different for each class?
Yes.
Would you say any particular class is getting better in chapter 4?
Well, the chapter 4 for one of my other classes is about rotational motion. Oh yeah, so the main 2 courses that I teach here regularly are 1000, which is physics for non-scientists, and 1500, which is physics for bio and chem majors. The question, or you're telling me you're a bio or chem major?
I'll
Okay.
finish.
1000 is very accelerated. We basically go through all the types of stuff from this semester and from 1510 in one semester, so that the students who aren't scientists at least are exposed to all the concepts, but it's very accelerated in that it's just very basic conceptual understandings and proportionally less math. 1500 goes through that over a whole year, going a lot deeper into all of the math. So that course is chapter 4, this course is chapter 7, rotational stuff. And then the physics majors in 1600, 1610, and et cetera, they go over those concepts over at least a year and a half. Because they have to do vector calculus and 3D math.
Sorry, I didn't mean to take away from her question.
Sorry, oh yeah, I'm getting very distracted today. I am very sorry. I believe the example you were asking about, the one we did in class, was this. Yes, so here all the angles don't match, and so a lot of different tensions all pointing in different directions. Main thing here is, the main similarity between this and the flower pot is still net force equals 0. So at any given point, we examined the forces directly on this thing, and then separately how all the forces add up here. At all points, net force equals 0. Here, that means that gravity down plus tension 1 up adds up to 0. Therefore, we can assume the tension up here should be equal and opposite to the weight of this object. At this point, it means that all 3 tensions must add up to 0, but since they are partially in different axes, we had to look at how their x-axis components add up to 0 and how the y-axis components add up to 0. So the main premise here is still the same. The main premise is everything adds up to 0. Examine how that works in separately the x and y axes. And usually, a different commonality is that the x components cancel out because there's only 2, and then the y components of these 2 team up against the first rope pulling down on the other end. And the flower pot is kind of the same, except the ropes are tied straight to the flower pot, and their y components are directly opposing gravity, and their x components cancel out. So the tensions are usually only the same number if angles match or if there's some other interesting relationship going on. Here all 3 tensions were different and all the angles are different, but the main relationship of the x-axis, everything adds up to 0. If there's only 2 things in a single axis, they must be equal and opposite. Did I address the concern? Okay. Now, I'll point out again, the way that this one went for us in class took a lot of lines of algebra. I write the test to not take a million lines of algebra. So if there is one like this on the test, I promise I have written it in some way to accelerate that process. Like I give you a new piece of information, or I set the angles in such a way that things work out more conveniently.
You said there was one very much like the flower pot on the test. I hope there isn't like this.
And maybe somewhere in between.
It is.
But again, there's something convenient about it that'll make it faster. Because again, the point is not just meant to be a 3-hour-long algebra slog. For that reason, keep in mind, I give points if you write out a paragraph answer. Like, it might not be full credit, but if you just tell me the concepts at play here, you'll get credit, even if it's words and not numbers. Never leave anything blank. In fact, the lowest score I've graded so far is because the test was mostly blank. Nothing but answers, wrong answers, and no work. So if you don't do that, you should be fine.
Did they still pass?
Question?
Yeah, that was the question.
Ah.
What was the lowest score so far?
I'm not going to give out a score,
A range.
or definitely not a name, and also not a score. I will say that if you give answers, even bad wrong answers, and bad wrong work, my scale is designed to get that ends up around 50 or 60. Again, if it is bad work and bad answers.
I'm just afraid I'm gonna type something wrong in my calculator. And it's gonna,
I think
give
I
me
broke
some
my
random
calculator.
answer. So I'm gonna try to write down everything, and I end up doing that all the time.
You should write everything
Yeah.
because, again, I can only grade what's on your paper, and everything that's written earns you points, especially if it's like correct work. I will also say it is still possible to get an A on this test, even if none of your final answers are perfectly correct. Like if you made an algebra mistake, getting between a correct setup and the answer, that's like 1 point off, maybe 2. Because this is not a course about doing all your algebra flawlessly all the time. This is meant to be a course about understanding the logic and the concepts. So if you set it up correctly, you've demonstrated the logic and the concepts, and if you make a mistake algebraing your way to the final answer, that is just the last tiny single piece. You could get a 90 on this test and technically get none of the numerical final answers right as long as all your setups were good. 90 is still an A in my book. Yes?
So you grade the answers as if, like, let's say one step right in the middle is wrong. So you grade the rest as if that middle step was correct?
Yes, I would say, if I can find one on the practice test that did something like that.
You did it wrong?
Well, no, like where you needed an earlier answer to figure something out.
Okay.
Yeah, let's look at this one for example. Because here, robot is doing a lot of work. Let's say that you miscalculate.
I did that last night. I put 20 instead of 200 in that first equation, like 500 plus 200. That's exactly what I did.
Yes, and let's just say that, here you calculate how much work, you try to calculate how much work the robot does. You, again, maybe plug in a wrong number and your answer for the work done by the robot is technically incorrect. Like that's 1 point off for making a math mistake. If you then need that number later on, like say, you then take that amount of work, bring it over here into the power formula to find time, as long as you use that wrong number correctly, you get full credit for that part. This is not double jeopardy.
What is the force after the W in the work equation?
Oh, this?
I don't know what that, like, it looks like it had 2 L's.
Those are parallel lines, because the force has to be parallel to the displacement. In this case, the robot is exerting force upwards and displacing upwards.
Okay.
If the robot was exerting force upwards, but the box was moving to the right, the robot's not the one doing that work. Something else is. And on the formula sheet, okay, on the sheet it is 2 lowercase l's. Oops. But it's meant to represent parallel lines, the parallel symbol.
That makes sense.
Okay.
For the third, for this one right here, you can, multiple times, like, we found delta y that way too, even though it says delta x, like, you can put delta y.
Yes. This formula is using the delta x just to stand in for displacement, and you can make that in the y-axis instead as long as all your vectors are y-axis. So, well, delta y, vi y, ay. Which, to demonstrate, is what I did in this one. Formula 3 is written down twice, once in the y, once in the x. Y-axis helped figure out hang time, plug that time into the x-axis version for displacement, yeah, horizontal displacement. Yes?
So just to prepare myself mentally, we're using that equation in this test.
Yes.
Which one?
We use that one.
Which-
This is, I honestly think, the most common of those first four equations.
The third?
Yeah.
Oh. Oh, yeah.
Not that one, but like the long, super long one.
Oh, this? Oh, yes.
Yes.
And actually, it looks like a student has already written it up here. And I'm just gonna leave it there. Because this class is not about memorizing that mnemonic, it's just using it.
So will it always give you a negative and a positive number?
Not always.
You always.
I'm glad you asked. Here are what the so these two times are both technically correct, it's just one of them represents an impossible scenario. This is the time after this point that the cannonball reaches a height of 0, and this, the negative one, represents a weird hypothetical point in the past. Like if time 0 is here, time negative 1.26 would be here. At a weird imaginary point where the ball launches from inside of the cliff and then passes this point with current speed 25.
Like, I saw one that gave both positive answers, but I don't know how you choose which one to use for the rest of the problem.
And I'm glad you asked. The main scenario that the quadratic can give you two positive answers in this type of question is actually if you end above where you start rather than below where you start. And it's just kind of a quirk of, you know, in this version, I plug in delta y as a negative number because you land below where you start, therefore it ends up positive over here and becomes positive inside of the quadratic. If you end above where you start, you'd plug it in positive here, it becomes negative on this side, and that changes the flow. And so this would give you two positive answers, and that's because those two different positive answers represent the two different times where the ball is at this height. Once passing it on the way up, and then once again actually concluding the process. So in both cases, they represent the two times where the object would be at that correct height. It's just here, one of those two times is a weird inside the cliff fantasy that takes place in the past. And here, the two times are one, while rising, and two, actually hitting the cliff. So in this case, you take the bigger of the two, the one that takes place further in the future when the event has actually happened. The event you care about has happened.
So it's pretty much always the positive form of the quadratic equation.
Unless you're looking for it.
Not necessarily, because here, the positive, if you use the plus sign, the way that this one is currently written, when you're descending, that's positive, so this would be a bigger number. The positive version would be subtracting a big number from a positive number and then dividing by a negative number. So in this version, the positive track actually gives you the negative answer.
Okay.
Because the absolute value in here spits out a positive, positive opposing a negative over a negative gives you a smaller negative. Then if you go the negative option, you add a negative to a negative and then divide by a negative, that would give you the bigger positive answer.
Okay, I thought they were done in order.
Well, yeah, I did positive followed by negative. And then over here, the bigger one, Yeah, here the bigger one should come from the negative option as well, because even ignoring the delta y being the opposite sign, the A term on the bottom would still be negative and it would swap whatever sign you had on the top.
So if that equation were for that problem that you drew on the board, would it be a negative 30 in the quadratic formula?
Yes,
Okay.
because it would start positive over here, become negative over here, and therefore C would be negative in there.
Okay, great.
Which means it has the potential to scream imaginary at you if you do something wrong. How you guys feel? At least not worse than earlier, I hope, right? Not worse? Okay. Primary mission accomplished then, for my opinion. Anything else on your minds presently? It's okay if not. Like, the point is to answer your questions. At a certain point, people run out of questions. The official time slot for lecture is pretty much over at this point. You're welcome to hang out if you want to study in the room or think you'll come up with a question shortly. But otherwise, you're also more than welcome to head out of here, eat lunch, take a nap, whatever behooves you. Definitely don't take a test on an empty stomach. I'd be miserable. Stick around if you want. You head on out if you want. I'll be either here or in my office. And let me know if you need anything, and I think you guys are gonna do great. And then once you're done, you just head on your fall break.
Would I be able to start the exam early?
Sure.
Just go ahead and get it over with.
Okay. You wanna do it right now, or you wanna come back in a second?
I'll do it right now.
Okay.